Tengan todos y todas muy buenas tardes. El Colegio de Ingenieros Civiles y la Asociación Costarricense de Geotecnia les da la bienvenida a la charla virtual del día de hoy, Cimentaciones profundas, tipos, instalaciones y métodos de ensayo para la evaluación de la integridad estructural y la capacidad de carga geotécnica, a cargo del instructor Mohammad Hussein. Antes de presentar a nuestro panelista, recordarles que pueden colocar sus consultas en la pestaña de preguntas y respuestas que se encuentra en la parte inferior de esta aplicación. Estas serán evacuadas al finalizar la conferencia. Por otra parte, la charla está siendo grabada y será colocada en el canal de YouTube del Colegio de Ingenieros Civiles, el cual los invitamos a suscribirse. Ahora bien, le doy la palabra al ingeniero Diego Cordero, a cargo de la Asociación Costarricense de Geotecnia, quien nos presentará a nuestro panelista del día de hoy. Adelante, don Diego.
Gracias, Carol. De parte de la Asociación Costarricense de Geotecnia y del Colegio de Ingenieros Civiles, les damos la bienvenida a la charla que va a impartir el ingeniero Mohammad Hussein. Quisiera, antes de darle la palabra, presentarlo. Mohammad Hussein, es miembro vitalicio de la Sociedad Americana de Ingenieros Civiles. Es ingeniero principal de la empresa GRL Ingenieros y director ejecutivo de Relaciones Globales con la Industria en Pile Dynamics Incorporated. Empresas antiguas y de mucho prestigio a nivel mundial, dedicadas respectivamente a los servicios de ensayo de cimentaciones profundas y a la fabricación de equipos especializados para dichas pruebas. Cuenta con más de 40 años de experiencia internacional y ha participado como consultor en más de 1000 proyectos de cimentaciones profundas alrededor del mundo. El ingeniero Hussein imparte como parte del programa de educación continua de la ASCE el curso Diseño y Construcción y Control de Calidad de Cimentaciones Profundas. La presentación de hoy se basa en las diapositivas y el material de dicho curso. El ingeniero Hussein ha sido presidente del Comité de Cimentaciones Profundas del Geo Institute de la Sociedad Americana de Ingenieros Civiles, así como del Comité de Educación de la Pile Driving Contractors Association, y actualmente preside el Comité Técnico de dicha asociación. Es reconocido con múltiples premios profesionales e industriales, ha sido autor y coautor de más de 60 artículos técnicos y coeditor de 10 libros de ingeniería. Posee certificaciones de nivel experto y está registrado como ingeniero profesional en los Estados Unidos. Mr. Hussein, the floor is yours. You can start when ready.
Thank you. Thank you, Carol and Diego, for the kind introduction. And thank you, everybody, for checking in today's presentation. I'll try to make the next hour of your time interesting and hopefully useful in your practice when it comes to Deep Foundations work. I thank you very much for your time, and I will start my presentation. Deep foundations have been used for centuries. Herodotus, the ancient Greek historian, mentioned the use of foundations 2,500 years ago. Just to give you an idea of the progress we have had in deep foundations over the many years, in 1648, when they built the Royal Palace of Amsterdam, they used 13,659 piles. In 2010, when they built the world's tallest building, 160 floors high, in Dubai, they used only 194 piles. Great progress we are having. The use of deep foundations in America, in North America, is said to have started with the invention of the skyscraper, the high-rise building that was first built in Chicago. This is the very first high-rise building built in Chicago in 1885, 10 stories, a steel frame building, and the foundation for which were hand dug. So they used to send people down into the ground to, by hand, by shovel, dig the foundation and then fill it with concrete. So this is one such foundation where they have an enlargement at the bottom, and they actually had an engineers meeting, a project progress meeting held at the bottom of one of these foundations. In today's practice, we use deep foundations to support all kinds of structures in all types of geotechnical conditions to resist all kinds of load combinations. They consist of driven piles, and there is a manual in 3 volumes, Design and Construction of Driven Pile Foundations, issued by the United States federal government, Department of Transportation. This manual was written by engineers in my company, general engineers. They wrote the manual that everybody uses throughout the United States for the design and construction of driven piles. At the end of the presentation, I will leave you my email address. If you're interested in these manuals, please send me an email and I will send you a link so you can download these manuals for free in PDF form. So we have driven piles, we have auger cast piles, cast in situ foundations, for which there is also a design and construction manual I can send to you, as well as drill shafts or bored piles. There's also a manual in 2 volumes for that. Driven piles typically consist of timber piles, concrete, and steel piles. Timber piles have been used for thousands of years. That's all we used to use is timber piles for a long time. Now, in today's practice, timber piles are used to support small structures or they're used as ground improvement technique. There is a manual for the design of timber piles as well you can download for free from the Timber Piling Council. Steel piles come in 2 varieties, H-pile and pipe pile. There are about 20 different H-pile sections, profile, specifically made for foundations. They look like H-beams, but they are not structural H-beams. They are specifically H-piles made for foundations work. Pipe piles come in a variety of sizes, ranging in diameter from a few inches to a foot or two, to a few feet, to maybe more than 10 or 15 feet, depending on the need. So they range in diameter and in wall thickness, and they also range in length. For example, if you ever come to Florida and you go to Disneyland, the foundations for these piers, for the monorail, one of them went down about 100 meters, 350 feet deep, 100 meters deep foundation. And also in Florida, we have piles that are 415 feet deep, like 130 meters pipe pile long. Pipe piles can be open-ended or closed-ended, and they can be uniform or they can be tapered, or they can be semi-closed-ended. So they can be designed depending on the requirements of the design of the project. One of the main advantages of steel piles is that they can easily be adjusted for depth, for length, by welding to add length or by simple torch to cut off. So if we have a variable subsurface condition, steel piles, H-piles, or pipe piles will be ideal foundation solution. The main disadvantage of steel piles is that they're susceptible to corrosion. They corrode. For that reason, when steel piles are designed, sometimes they are coated with material in order to prolong their service life, and sometimes they also add artificial thickness. They make the thickness a little bit extra in order to account for the corrosion effect. And there are in the manuals, there are design tables how to expect how much corrosion you can have and how we can protect it with cathodic protection. For offshore applications or near shore for ports applications, harbors, offshore, steel piles are exclusively used. Steel pipe piles are exclusively used. The other kind of piles we have is concrete piles, mainly pre-stressed concrete piles, typically square, pre-stressed concrete piles. We may also have post-tensioned cylindrical concrete piles. The pile will have to be cast in the casting yard and transported to the project site. On the project site, they can also be spliced, either by epoxy dowel splicing or by mechanical splicing. If the pile is very large, like more than 24 inches on the side, then they make it hollow in order to make the weight less so the pile can be handled with ease. There are design manuals specifically from PCI for the design of pre-stressed concrete piles that you can also download. The newest addition to the use of concrete piles is the utilization of ultra-high performance concrete. This is the very first such pile driven. The strength of this concrete is 4 times the strength of normal concrete. So while piles may be uniform and prismatic, they don't have to be. They can be highly non-uniform in cross-sectional profile along their length, and they can be composite, made out of more than one material in a variety of combinations. There are many, many different hammer models, hammer types, hydraulic hammers, air steam hammers, diesel hammers, single acting hammers, double acting hammers. There are hundreds of different hammer models available, from the very small to the very large, to drive these various kinds of piles. So we typically drive piles one pile at a time into a pile group to make a foundation to support a bridge pier, for example, or a building or some kind of a structure. To support the building, we need to know the pile's static load bearing capacity, how much static load the pile will be able to support. The best way to evaluate the static load bearing capacity of a pile is by performing a static load test. Static load testing can be performed by using dead weight or reaction piles or combination of the two in order to support this reaction beam. Then we put hydraulic jack on top of the pile and we apply load, static load, and we measure the corresponding pile top movement. So this is a typical static load test result, load versus movement. Please keep this in mind. Remember this. I will bring it up again later. So this is a typical result of a static load test. To get more information, we may want to put strain gauges along the length of the pile and measure the load transfer between the pile and the soil with these strain gauges versus depth. So that will allow us to separate how much skin friction we have and how much in-bearing resistance we have during the static load test. So this is great. However, it's the best thing we can do, but it has many limitations. Static load testing costs a lot of money, and also it takes a lot of time to perform. Also, we have to be mindful of the safety when we perform static load testing, whether we use dead weight or reaction piles. So very, very important limitations. That is why we do not do so much static load testing. Also, very important, when we drive the piles into the ground, we do not have much time between driving of the pile and then building the structure on top of the piles. So not much time to run static load test. And if we have a project over water, then static load testing is much more expensive. So the challenge that we have is, can we obtain the static load bearing capacity of the pile from information during pile driving? Can we relate the static load bearing capacity of the pile to its driving resistance under the driving of the hammer? Can we in fact find a relationship between the pile driving, blow count, blows per meter, and how much tons static load the pile can take? Can we in fact quantify this non-linear relationship between pile driving blow count during pile driving and static load bearing capacity of the pile? That's a challenge. For a long time, people involved in pile driving realized the relationship between the energy of the hammer and the load of the pile and the blow count. So if it takes a lot of energy, a lot of work to drive a pile into the ground, then the pile will carry more load. So Mr. Wellington in 1888 wrote an article in the Engineering News magazine relating the pile load bearing capacity to hammer energy and penetration under the hammer. So we call this the E&R formula, E&R approach, energy approach. Many people try to improve on that simple equation But of course, no matter how much they try to improve it, when in 1888, in the 19th century, we only drove very short timber piles, only with drop hammers. Now, of course, we have much, much larger hammers, much longer, flexible, elastic piles, much more complicated lengths and penetration and high loads. So applying 19th century technology to today's practice is not very effective and it's not advised. So in the 1940s, a Mr. Smith, Edward Smith, realizing that the dynamics of pile driving under the hammer is better represented by stress wave mechanics. When the hammer impacts the top of the pile, it generates a stress wave that travels down the pile length back and forth very fast, like 5,000 meters per second stress wave inside the pile, but finite. Mr. Smith wrote a computer program utilizing the wave equation. This is the second order differential wave equation to apply to the stress wave in the pile. Mr. Smith called his program the wave equation analysis of pile driving. This program that Mr. Smith wrote in the 1940s, 1948, is often cited as the first program in civil engineering. The very first program that anybody wrote for civil engineering application using the digital computer is this program that Mr. Smith wrote for the pile driving dynamics. Mr. Smith wrote the program for use inside his own company only, Raymond Pile Driving Company. Then the United States government, they commissioned our group, GRL, to write a public domain program so the public can use wave equation analysis. This program is called GRL WEAP, and then it is promoted by the company Pile Dynamics. Wave equation analysis is a computer simulation program that uses numerical methods in order to study, to evaluate pile drivability. So it's a very powerful program that relates pile driving blow count to pile load bearing capacity. So this is good information because then we can give that to the pile driving inspector on the job site. So the inspector will have a pile driving criteria for blow count, so many blows per meter, to make sure that every pile is driven to the required blow count to achieve the required ultimate load bearing capacity of the pile. They do that utilizing this equipment called saximeter, meter of sound, that listens to the pile driving hammer, and then it tells you blow count and the pile capacity from the criteria. So while it's a very powerful program, it's a simulation program. It's computer analysis by simulation. It relies on assumptions. The analysis engineer has to assume many parameters to build up the model inside the computer. That is why it has potential sources of error, because it is based on assumptions. So the same engineers who wrote the program thought, what if we take measurements? We go to the job site and we perform measurements. And we analyze the measurements instead of assuming parameters and information. So we measure the information we need and we analyze it to come up with the results. This dynamic pile testing measurements started in 1960s at Case Western Reserve University in Cleveland, Ohio, headed by Professor George Goebel, the one standing up there in the lead, assisted by then graduate students, Drs. Frank Rauschi and Goran Likens. Goebel, Rauschi, Likens, GRL. That's the name of the company later on. So Goebel, Rauschi, and Likens, they invented the whole idea of dynamic pile testing during pile driving. They invented all of the equipment, the sensors, the gauges needed. They invented the computer to analyze the data on the job site, and also they invented the formulas, the equations that are needed to analyze the measured data. And they showed during the research good correlation between the prediction of static capacity of the pile from dynamic measurements and actual static load test. So later on, the equipment that was used during the research had been shrinking down. So now dynamic testing, 50 years later, is performed all over the world using this equipment called Pile Driving Analyzer and software called CapWeb. CapWeb is a wave equation analysis that uses measured data from pile driving analyzer as input. No need for assumptions. So we measure what is needed and we analyze it on the job site. So let's start from the beginning. This is static load test. We need all of this dead weight because we need to perform static testing. So what if we were to do it differently? If we were to take a small portion of that, a small piece, put it in a guide, lift it up high enough and drop it so that that will produce the same load on the pile as all of this weight. So that is the difference between static load testing and dynamic load testing. The pile driving hammer provides a dynamic load test load. So all we have to do is to put sensors, put gauges on the pile, and then we can perform dynamic load testing. No need for static testing. We can perform dynamic testing during pile driving. This is done through ASTM standard D4945. Testing can be performed with a testing engineer standing there on the job site, or it can be done completely remotely using site link technology with the satellite link. So the equipment will send the data to the test engineer anywhere in the world in real time during pile driving, remote testing, remotely. So dynamic pile testing is a measurement of load and movement of the pile under the impact of the hammer, and the analysis of these measurements utilizing stress wave mechanics, elastic, one-dimensional stress wave mechanics. Load is measured with strain gauge, and movement of the pile is measured with accelerometer. These are very small instruments, only like 10 centimeters, reusable, and they can be attached to any kind of pile, pipe pile, H pile, concrete pile, timber pile, as well as cast-in-place foundations like board piles or overcast pile. So when the hammer hits the top of the pile, the stress wave is generated. When the stress wave goes by the gauge location, the gauges will sense a quick rise of force and movement of the pile. Then the stress wave travels down the pile length to the pile bottom, reflects, comes back, and we see the reflection. So this is data from one measurement, one impact, one hammer blow, showing impact and reflection at the pile top. We will take this every blow. So during the pile driving, we will do a dynamic test under each blow. If we look on the bottom left side of the table, we see this pile. It took 1,813 blows. So this pile was tested 1,800 tests during pile driving. These results can be done in table form, also in graphical form. Versus penetration depth, we see that the compression stress on the pile, tension stress, the energy of the hammer, and the static load bearing capacity versus depth, and the blow count versus depth. So it is complete test record during the driving of this one pile, done on the job site in real time during pile driving. The information can be used to analyze the hammer, pile, and soil. Analyzing the hammer is very important because we measure the energy received by the pile. We compare the energy received by the pile to the maximum energy of the hammer. And we see that that can be highly variable. It can vary. Maybe the pile only receives 10%, 20%, 30%, 80%. It could be anything. So we have to quantify the efficiency of the hammer because we are using the pile driving blow count to evaluate pile capacity. Why does it vary so much? Why is it so low or so high? Why does it vary? That is because it depends on the mechanical condition of the hammer and the state of maintenance of the hammer system and the various components of the hammer system. When the hammer hits a pile top, the pile undergoes a very complex state of stresses that includes compression, tension, shear, torsion, bending, all kinds of stresses. These stresses sometimes they damage the piles. Piles may be damaged on the top, but by taking measurements, we are able to measure the stress and limit and eliminate the damage, the cause of the damage by reducing the energy of the hammer. So even though it's measurement only on the top of the pile, we can calculate from the top measurements the stress at any location along the pile length, including the bottom of the pile, because the bottom of the pile stress may be twice that on top of the pile. So when we drive piles to hard layer, notice no damage up on top. But when we extract pile, we have pile damage at the bottom of the pile because of the too much stress at the bottom because of end-bearing resistance, end-bearing reaction in the pile. Also, during easy driving, the pile will have tension stress that may crack concrete piles. So when we have damage on the pile, this will send back data, will send back reflection that will get registered in the pile top record that we measure with the PDA. So early reflection in the data indicates damage on the pile. Here we see concrete pile damage, and here we see steel pile damage. So the PDA, the pile driver analyzer, will calculate the location of the damage and the amount of the damage along the pile length. So we talked about hammer performance and pile performance. Now, soil performance. When the hammer impacts pile, the pile moves on the ground. The pile movement activates soil resistances. So now we have two waves on the pile. We have the wave going down from the hammer, and we have the wave going up from the soil. Both of these waves are at the gauges that the PDA measures. So the PDA under each hammer blow will measure the wave going down the pile from the hammer and the wave going up the pile from the soil. From these reflections of the stress waves of the soil resistances, then we are able to resolve them into skin friction distribution along the pile length and end-bearing resistance during pile driving under each hammer blow. Testing can be done during initial driving and later in restrike to study the setup effect, increase of pile capacity with time, setup, or decrease of pile capacity with time. It's called relaxation. We can then put the measured data from the PDA into the CapWeb analysis software program that uses sophisticated pile-soil interaction model with signal matching analysis technique in order to come up with the skin friction distribution along the pile length, and then we can simulate load versus movement. Remember, I asked you that we will talk about the load versus movement. Now it is not from load testing, but from dynamic measurements. So under the impact of the hammer, measurement with the PDA and analysis with CapWeb, we can simulated load versus movement, load test. How good is that? How does that compare to full-scale load test? So there have been many studies. This is a case history paper published by ASCE showing excellent correlation. And this is another paper also published by ASCE, also showing excellent correlation between simulation from PDA measurement and actual static load test. So engineers can use dynamic testing on test pile program on a few piles in the beginning of the project in order to establish production piles length for the job, establish production pile driving criteria, also to check on the engineer's assumptions, design assumptions, and also to check the contractor's equipment and means and methods. Alternatively, recently, projects now are using 100% testing. Every pile on the project is tested with PDA. The state of Florida now, every pile for the highway department is tested 100%, every pile on the project. They found that optimizes construction efficiency and economy and increases engineering reliability. Dynamic testing can also be used to other kinds of deep foundations, not only driven piles with a hammer, but also helical piles or micro piles. All we have to do is bring in drop hammer and hit the pile and perform dynamic load testing, including testing of cast in situ foundations, cast in place deep foundations, including auger cast piles that are used now to support buildings and bridges, all kinds of foundations, auger cast piles. They're constructed using continuous flight, hollow stem auger, by drilling the hole in the ground, filling with grout, and pushing the steel cage, or by using this equipment where we displace the soil in the ground, displacement kind, cast in place, auger cast pile. The equipment to construct these piles is fitted with this instrumentation during pile installation that measures the grout volume, the auger depth, grout volume, pressure, torque, in order to make sure that every pile is constructed properly. Drill shafts is another type of deep foundation, cast in place, typically very large, maybe 1, 2, 3, 4 meters in diameter, 25, 50 meters deep. They are usually used to support very large structures and very heavy loads in axial loading and also in lateral loading. The beginning of using a drill shaft foundation started in the 1930s in Texas as an outgrowth of the oil industry. So they take one auger and they drill hole in the ground looking for oil. If they find oil, great. If no oil, then they fill it with concrete and make it foundation that the Texas Highway Department started using for their bridges in the 1950s. In Florida, they started using drill shafts for bridges after the first bridge in Florida collapsed by ship impact. So if the water table is very low, we can drill a hole, look down it, put steel cage, and fill with concrete. If the water table is high, we have to use steel casing, steel pipe, either temporarily during construction or permanently as part of the constructed shaft. Or maybe we use slurry. Slurry is a heavy liquid we put in the hole to exert hydrostatic lateral pressure so the wall of the hole does not fall during the construction of the drill shaft. So now we have a hole full of slurry. We have to fill it with concrete. We do that from the bottom up. For that, we use a tremie pipe. So tremie pipe, very long, the length of the pile. We take it all the way down and we fill it with concrete from the bottom and we collect the displaced slurry up on top. The bottom of the tremie pipe must always be inside the concrete. If it goes outside the concrete, then we will have a problem with the integrity of this shaft. The steel cage and the concrete, they have to be designed so that the concrete will go through the steel cage in order to engage the side of the hole to give us a geotechnical skin friction resistance. So when we drill the hole, we have to inspect it. We have to inspect the hole for profile of the drilled hole and the verticality, plumbness. We have to drill a perfectly plumb hole. We also have to check for the cleanliness and the competency of the bottom of the hole for end-bearing resistance. We do all of these inspections before we put the steel cage in the hole and before we put the concrete. The hole profile and verticality are checked with this equipment called SHAPE, ASTM standard D8232. SHAPE equipment is electronic equipment. We send it down in the hole, even inside the slurry. We send it in the hole. It sends out signals, waits for reflections, so that will allow us to draw a 3D picture of the drilled hole. So we have a 3D picture of the drilled hole and the verticality or off plumbness of the drilled hole and the offset between the bottom of the hole and the top of the hole to make sure that it is within design tolerance. It will also calculate volume of drilled hole. This is very important because later on, when we put concrete in the hole, we have to make sure that the volume of concrete we use is equal to the actual volume of the drilled hole, not theoretical hole, but the actual hole as we drilled it. Very important. That the cleanliness and the competency of the bottom of the hole so that we have to measure so that we do not have any loose material or debris that will affect end bearing of the drill shaft. We do this inspection testing with this equipment called SQUID, Shaft Quantitative Inspection Device. It has 3 little penetrometers that we push into the bottom and we measure the thickness and the strength, the stiffness of the material to make sure that the bottom of the shaft is clean to allow for end bearing of the drill shaft. So we do the inspections and we do the construction, and the constructed shaft may be good, maybe perfect, or not so perfect, but maybe good enough, but sometimes it will have serious problems. So now we have to check for integrity. There are many factors that affect the integrity of the constructed shaft in the ground. They include subsurface conditions, design, installation methods, and workmanship. Very important. There have been many studies done all over the United States by various universities, highway departments, agencies, owners, consultants, and they found that many of these gas in place, gas in situ deep foundations have some kind of structural issue. The oldest way, and maybe 50-year-old now, to test for integrity is PIT, low strain pile integrity testing, ASTM standard D5882. That uses the impact of small hammer to send a low intensity, low strain wave down to the shaft and back up. So we measure on top of the shaft the impact and the reflection from bottom of shaft. So this is impact and reflection from bottom of shaft 25 meters long. Good data, good shaft. This data is not so good, and the shaft has a defect at 15 meters. Shaft length 25 meters. At 15 meters in the shaft, we have reflection. So this reflection indicates that this shaft has defect. We can analyze this data, and we can try to quantify the location of this defect along the length of the shaft. So this is the first technology, the first testing for integrity assessment. Very old and has many limitations. I also want to say that this type of testing can be performed to test for length of unknown length of piles in service. For example, for scour studies, for load rating, for bridges, for buildings, that the pile foundation length is not known, this test can be performed for that purpose. You have a 50-50 chance of having good data for many reasons and limitations. The next test method is called CSL, cross-hole sonic testing. Much better than the previous test, PIT method, but more involved. To perform this test, ultrasonic testing, CSL, ASTM D6760, we have to cast these access tubes, 1.5 inch diameter access tubes into the shaft. And then we have equipment. We need to have transmitter, receiver, so we can scan. And then we have to have a depth encoder, and then the equipment and engineer on the job site. So we cast these access tubes, small diameter steel access tubes, into the steel of the shaft, and then we take them two at a time, and we send signal from one and receive it as the other. So we scan between these two tubes, many scans between two tubes. The number of scans we can have is n squared minus n over 2. N is the number of tubes. So for a 5-tube shaft, we can do 10 probes, 10 different profiles. The number of tubes needed is equal to diameter of shaft in feet. 5-foot diameter shaft, we need 5 tubes. So when we send the signal from one tube to the other, we receive it in the tube. If we have good concrete, the signal is received well. If we have defect between the tubes at a certain depth, that defect will delay the signal and weaken the energy. We send signals every 5 centimeters. So we may have a shaft that is 25 meters long. Every 5 centimeters, we send a signal. So we can stack them. We can put the signals, color code, green, black, and we put them on top of each other. So this is the result of CSL test on the left-hand side between these two tubes. So this shaft has 4 tubes. So we take 2 tubes, and this is a scanning between the 2 tubes. Good looking data, no problem. The data in the middle between the other tubes shows we have defect in the middle of the shaft, and on the right-hand side, we show that we have defect at the bottom of the shaft between those 2 tubes. So between the various tubes, we see where we have defect at what depth. We can put all of this data from different tube scans into 3D tomography program that will show us the 3D picture of the defects inside the drill shaft, inside the steel cage of the drill shaft. So much improved over the PIT method. However, it has its limitations. We have to wait maybe 5 days or more for the concrete to cure. Otherwise, we will have bad data. The access tubes we need for the test may debond from the concrete. That will give us bad data. If we use steel casing, that will give us bad data. Many reasons to have bad data with this test. Also, this test will only see defects inside the steel cage. So this is defect, styrofoam defect we put inside, and then we put concrete, we test CSL, we can see it inside. But if we put defect outside, we cannot see in the TSL test. So many limitations. The newest method for integrity testing is the thermal integrity profiling. This is the best method for integrity testing of bore piles, drill shafts, ASTM standard D7949. Tip method, thermal integrity profiling tip, relies on the measurement of the temperature of the concrete inside the ground, inside the drill shaft, during the curing process. The temperature is measured using thermal wire that is attached along the length of the reinforcing steel cage. Every 30 centimeters, every foot, we measure temperature, and we put many around it. The number of wires needed is diameter of shaft in feet. So 4-foot diameter shaft, 1.5 meter diameter shaft, we need 4 wires. And we take measurement around and versus depth. We know that because of the chemical reaction, the cementation reaction of the concrete generates heat. This heat can be very, very high, 2 times, 3 times the temperature of the ground. So we can have the signature, the heat signature profile of the shaft that we can use for assessment of integrity. This testing is done completely automatically. No testing engineer is needed on the job site. The thermal wire is sent to the job site. The contractor will simply attach it with tie wire to the steel cage and construct the shaft. Then these thermal devices, they take temperature and they send the data through the cloud to the engineer in the office, anywhere in the world, to the engineer, to the contractor, to the agency, to the inspector, will get the data every 15 minutes. During the curing process for 24 hours, the test is finished and the integrity of the shaft is known automatically, completely automatically, a completely self-tested shaft. So if we have a drill shaft and we have a localized defect at a certain location will produce a localized reduction of temperature. If there is no reduction, then the temperature is not changed. If the concrete changes, then the temperature changes also. So a localized defect will produce a localized reduction of temperature. Furthermore, if we compare the temperatures along the length of the shaft on one side of the steel cage to the other, and we see that one side is always more temperature than the other side, this will tell us that the steel cage had shifted inside the concrete because one side is hotter where it's closer to the center and the other side is cooler closer to the soil. So from this information then we are able to draw a 3D picture of the concrete profile, defects, and also of the location of the steel cage inside the concrete to make sure that we have enough cover. So this is data, 10 wires along the length, color-coded, temperature on the left-hand side. So this tells us that at 90 feet depth, wire number 7, 8, and 9, color-coded, have a defect. So we can convert the temperature measurement on the left-hand side to equivalent concrete reading in the middle that will allow us to draw 3D picture of the drill shaft in the ground. The same temperature measurements can also be used to assess, to evaluate integrity of barrettes and diaphragm walls in the ground. This technology of temperature measurements to assess, to evaluate integrity of deep foundations is so innovative that it had won many innovation awards from ASCE, DFI, and many organizations in the United States. So we talked about integrity testing, low strain testing with small hammer. Small hammer impact will tell us something about integrity. but nothing about load-bearing capacity. To test for load-bearing capacity, we need to perform high-strain testing. To perform high-strain testing, we need bigger hammer. We need to have hammer big enough to impact the board pile, to move it against soil resistance so we can measure load-bearing capacity. So how big should the hammer be? Depending on the size of the board pile and the load. The hammer weight, the drop hammer weight we need to perform this testing is equal to 2% of the load we are trying to test. If we have to test this pile to 1,000 tons, we need 20-ton drop hammer. So we can bring in drop hammer, we can put instruments on the pile, or we can use a load cell. We can attach the accelerometer and the strain gauge. We can measure load and movement like we do with the pile on the pile, or we can put load cell under the hammer on top of the drill shaft or board pile, and we can take measurements. So we can perform dynamic measurements by hitting the board pile, the cast in place foundation with a drop hammer. That will allow us to then measure the wave going down the pile, the wave going up the pile with the PDA and do dynamic testing. This is an excellent picture because it shows that this contractor was required to perform a load test on this board pile, drill shaft. He decided to perform dynamic testing, not static testing, dynamic testing. And then he knows the weight of the hammer, 2% of the load. So he manufactured the hammer on the job site using the same concrete. And then he made this drop mechanism to perform the testing. So he performed this load test on the job site for practically no cost, very little cost, very economical to perform this dynamic testing on the drill shaft. So when we have a drill shaft, when we impact with the hammer, we have reflection from soil resistance. We also have reflection from the shaft non-uniform. So non-uniformity of the shaft will also send back wave reflections. So what we're going to do is we're going to take the profile of the shaft from the thermal wire and put it as input into the program, so that way we can account for the non-uniformity of the shaft when we analyze the soil resistances for more accurate analysis. So we can then use the dynamic test by drop hammer on drill shaft. We can use the profile of the shaft from the thermal measurement to come up with load movement of drill shaft simulated by dynamic measurements without having to perform static load testing. So this is static load testing. This is conventional shaft top static load testing. ASTM standard D1143, static load testing. We need to put this reaction beam because we need to put this hydraulic jack on top of the pile, on top of the shaft to perform top-down static load testing, conventional testing, in order to obtain the load versus movement. That is why we need to use so much dead weight or so much reaction piles to hold the reaction beam in place to perform static load testing, conventional. A very smart professor, Professor George Osterberg, invented a method to put the hydraulic jack at the bottom of drill shaft. And he called it O-cell, Osterberg cell. Professor Osterberg load cell, O-cell. That way, we do not have to have reaction weight. We only put the load cell on the bottom of the drill shaft. So Professor Osterberg passed away. The patent on his invention expired. So now we do not call the test O-cell test anymore. We call it bidirectional static testing. ASTM standard D8169, bidirectional static testing. This engineer is performing static load test, full-scale static load test on this drill shaft. Nothing up there. Everything is in the ground. So this is how this test is performed. We will put the hydraulic jack on the bottom of the shaft and we apply load. And then we measure movement of the shaft up, skin friction, and down in end bearing. So apply load, x-axis, we apply load, and we measure movement up in skin friction and movement down in end bearing. We apply more load, we measure more movement. We apply more load, we get more movement until either skin friction is fully mobilized and fails, or end bearing will fail. In this case, skin friction failed. At this time, the test is finished. So therefore, the maximum load we can use this testing for is equal to 2 times the minimum of skin friction or end bearing. That is why sometimes they move the location of this load cell into the body of the shaft in order to have more load to test for. Skin friction above, skin friction and end bearing below to have more load to test to. We can take this data, the measurements at the bottom of load versus movement in skin friction, load versus movement in end bearing, and convert it into an equivalent shaft top conventional loading by simulation. So from the measurement at the bottom, we can simulate a load test as if we have loaded the shaft conventionally from the bottom using reaction weights. So whether we perform dynamic testing with drop hammer, full-scale static load testing with reaction weights, or bidirectional load testing on these board piles or drill shafts, the drill shaft has to be instrumented with the thermal wire because we need to know the profile, the actual profile of the shaft in the ground, not the theoretical shape, the actual shape, in order to make sense of the load test data. All of these tests I explained today are widely available in standards, codes, specifications, textbooks, reference books, conference proceedings, academic dissertations, theses, technical papers. There's much information out there on the basic principles, applications, limitations, and use of all of these test methods I described to you today. These test methods are all manufactured by Pile Dynamics and are used by GRL engineers. And we are located in Cleveland, Ohio, United States, with offices all throughout the United States and also worldwide, anywhere in the world. All of these equipment I described to you today are either invented or now produced by Pile Dynamics, our company, Pile Dynamics. Manufacturers, and we sell all of this equipment. Our sister company is GRL, which is consulting engineers that perform field testing utilizing all of this equipment. So I think, Diego, we have a few minutes left for any questions. I will try to answer all of them. If we do not get to all of them, or if any questions come to mind later, this is my email address. Very easy to remember, mhussein@pile.com. Please send me an email. I'll be very happy to reply, to engage in discussion about anything you may have to do with foundations, deep foundations, and testing. With that, I thank you for your time today. I appreciate the opportunity to present to you. I hope you found the presentation interesting and useful.
Thank you, Mr. Hussein, for your lecture. Carol, no sé si hay preguntas en...
Sí, hay dos preguntas. Las dos están en inglés.
Okay. Mr. Hussein, can you see the Q&A box?
No. Can you please, can you read the questions, please?
Okay. The first one is, thank you very much, Mr. Hussein, for such informative lecture. It's a share. I guess it's a shame it is a 1 hour length only. Could gravel columns be considered a kind of deep foundations? What are the methods for construction and testing recommended for gravel columns?
Grouted columns, the testing that can be performed is the thermal profiling in order to get the profile and plate testing. There is no dynamic test that I know of for grouted columns. If I understand grouted columns as a cement mix in the ground, if that's my understanding.
Okay, thank you. There's another question. It says, well, thank you for your presentation. I would like to ask if there is any difference using the transient response method or PIT, measuring the hammer impact force and the pile head motion for evaluating the pile integrity.
Excellent question. So the PIT method as I showed it, uh, so the PIT method, as I showed it, I showed it in the time domain, which means that the data shows the impact and reflection in time or in distance domain. The same data can also be analyzed in frequency domain, which is called the transient method. Basically, it is using exactly the same data to present it in two different ways, either in the time domain or in the frequency domain of the components of the measurements. Basically, they both give you the same information because they are both based on the same exact measurement, only presented differently, whether in time domain or frequency domain. I hope I answered your question.
Yeah, I think you did. And a last one, it says, well, test for lateral loads in piles in ports. I guess they're asking for information for lateral load testing.
As far as I know, for lateral testing, static testing is the only test that is available. There is no dynamic test for lateral testing. And what is typically done is they take two piles and they test them against each other laterally.
Okay. And there's a last one. It says, do you know the impulse response non-destructive test on piles?
Can you repeat that, please?
It says, do you know the impulse response non-destructive test on piles?
Yeah, this is the impulse response is basically the PIT pulse echo method. So the impact and the reflection, the pulse response. So that's typically what is referred to as a low strain test method, either by the time domain or by the frequency domain. But my understanding, this is what is referred to, is this low intensity impact, small handheld impact hammer test.
Okay, thank you. Okay, there's one more coming in. It says, using PIT for an existing pile, do you need access to the pile top or can you perform the test laterally? What is
No,
typically done if you have a
no.
pile cap?
You do not need access, although having access is best, but you do not have to have access to the very pile top, and you do not impact it sideways. You see the engineer here on the right-hand side of the picture. The accelerometer, the measurement is done on the pile, and impact with the hand hammer is applied up on top of the cap. And on the left-hand side, the engineer there standing on the bucket, putting the sensor on the pile, and then that will impact the top of the cap. So you can apply an axial compression impact with the hammer impacting something on top of the pile. And this is one of the reasons I mentioned that you only have a 50-50 chance of having good data for this, because when you apply that impact up on top of the pile, the stress wave goes on any other component of the structure, as well as it reflects back and forth within that cap that will affect the measure on the pile. So even if you were to impact the pile itself, the impact will send a stress wave in the pile down, which is good. It will also send a stress wave up that rebounds from the elements and components above. That will affect the measured data. So the best way to do it is to take measurements and you see if they're usable or not. You cannot tell ahead of time if the data will be useful until you actually obtain it, unfortunately. But yes, you can perform the test without having access to the very top of the pile. You can impact somewhere up on top and generate a stress wave that goes down the pile length.
Thank you very much. There's one, well, that's all the questions that we have so far. I want to thank you, Mr. Hussein, for your time and your presentation. It has been of great interest to all of us. And thank you, and hopefully we can have you in Costa Rica sometime soon.
Thank you. I look forward to it. And thank you again for the opportunity to present to you today. Have a good day.
Thank you. Agradecerles también de parte de la Asociación Costarricense de Geotecnia a todos los participantes. Muy contentos de ver colegas ingenieros estructurales e ingenieros civiles que han mostrado interés en este tema tan interesante.
Muchísimas gracias a todas las personas que se conectaron el día de hoy. Les acaba de pasar una pequeña encuesta para que por favor nos ayuden a llenarla antes de salirse de la aplicación. Y sin más, entonces damos por finalizado.
Muchas
Thank you,
gracias,
Carol.
Carol.
Con
Thank
gusto.
you.